So good morning, Professor. I am Sheshavarpu Yashwant. My UBI ID is 50464540. So today I'm gonna present my final project here. So what I'm gonna do is the first thing I'm taking a data set and running some hypothesis tests on it and visualizing the data and running some hypothesis tests on it, and then running applying a linear model to it and see the what are the results we are getting it, and what inference can we take from the data set, and then running an ANOVA test on it and applying central limit theorem to it. So like this, I'm gonna apply some topics and discuss about the results. So now I'm gonna share the screen. Um, I'm sharing the screen. So as you can see now, so first taking the data set, I'm taking a data set called MTCAS. MTCAS is an inbuilt data set in R. So let's see what data set consists of. Like using this command called question mark mtcars. By using this command, we can see it run. We can see the description of the data. So basically, our data is called motor trend car road tests. So the description is the data was extracted from 1974 Motor Trend US magazine and comprises fuel consumption and 10 aspects of automobile design and performance for 32 mobiles, which are the models are in between 1973 and 1974. So the name of this dataset is called empty cars, as we already saw. So the first thing, data frame with it is a data frame with data frame is nothing but a data set with 32 observations and 11 variables. So we have 11 variables here, and the first variable is mpg, which is miles per gallon, which is nothing but fuel consumption. And second variable is CYL, which is number of cylinders. Third variable is DISP, which is called displacement. Fourth variable is HP, which is gross horsepower. Fifth one is DR80, which is rear axle ratio. Sixth is weight, which is denoted as WT. Seventh is QSEC, which is 1 by 4th mile time. Fifth is VS, which is nothing but engine shape. If it's 0, it is V-shaped, or if it's 1, it is straight. Then ninth one is AM, which is transmission. Like if it's 0 means it is automatic transmission. If it's 1, it's manual transmission car. Then the 10th one is gear. The number of forward gears, let it be like 3, 4 like this, 5. And the 11th variable is carb, CARB, which is number of carburetors. So um, this is our data set. Now we are gonna work on this data set. Let's dive into this. So first thing, what I did is I've loaded the data set using this command, data called empty-car, which is like loading the data set and data set. And second one, I'm assigning the data set empty cars to the D. And third one, the third thing is head of D. Head of D means it gives us some top 6 or 7 rows in our data set, as I'm going to show you now. Clicking run, now we can see the head of the data: Mazda RX-4, Mazda RX-4 Wagon, Datsun, Hornet Sport, about Valiant. So these are the like models which are 32, but it shows only 6, as I told you. Head does, and this MPG CL displacement for the respective cars here. As we already discussed, these are the variables, and this is the model names. So next thing is we're gonna see what is the dimension. Like to conduct any test, we have to first thing know the dimension of the data set. So dimension of the data set. By clicking dim of d, we'll get the dimension of the data set. So next thing is that, like, to perform any operation, any test, to apply any model, first we have to take null values outside from the dataset. So to take null values outside from the dataset, the first thing is we have to see is if the data sets, if any columns are having null values or not, like what columns are having null values. If some column have more null values, it may not perform well due to that variable. So using this command, we can see the data set, see the null values in columns of data set. Yes, that's it. Clicking at run. Now, as you can, 32 by 11 is our data set dimension, and each column names are here, and these 000 are like number of null values in this. So we don't have any null values in our data set. So next command is str str of empty, because str structure tells us the structure of the data set. Like wait, as you can see down, it gives us the structure of data set. Like it gives us the data set variables names here, and this 21, 22, 22 are the structure. Like it gives out a vector of values for each variable here. As you can see, cylinder 66644 as it is. So this gives us a basic information about the data set again. And now this is the main thing here, and this is summary. What does summary give? Summary gives some important like important things which are useful for the hypothesis, like mean, median, quantiles, and all, um, for every column, like for every variable. So as you can see it here, I'm going to run it now. 1 second. I'm going to run it. So I ran it. As we can see is MPG. The minimum value in MPG is 10.4. The first quantile value of MPG is 15.4. The median of MPG is 19.2. The mean of MPG is 20.1. The third quantile of MPG is 22.8. The max of MPG is 33.1. So from these values, we can make many tests. Like we can come to an inference. Like we can take inference, like from how much value to how much value MPG is varying on. Like what are the most type of cylinders which we are using? What is the minimum displacement and maximum displacement? What is what is an average displacement? So these all we can infer from the summary of it. So this is the main thing. So this is about the data description. So next we are going to data visualization. So now we came to data visualization. So first thing, so what is data visualization and what part it does in assessing the data? So data visualization is an important thing in what is it called, data analysis, because we can know how the data is flowing in the, like, from which value to which value. So and then how the data is related to another, how one variable data is related to how to the another variable. So like this we can get the relations of variables between the variables, between different types of variables using different types of plots. Like we have many plots in data visualization, but majorly we use 4 or 5 plots to get the relations between the variables. So the first thing in our data set, there are predictor variables. Like I'm gonna go back a second. Just I'm gonna show you. So what is, we have 11 variables here. So what we have to get from this data set? So the one thing is like MPG is a fuel consumption, which is getting affected. We should see that if is the fuel consumption getting affected by other variables. Like one should be the target variable, and others are predictor variables. So in my data set, we have MPG is an target variable, and other variables are predictor variables. We have to see that is MPG varying when we, what is called varying due to other variables like number of cylinders, displacement, horsepower, and all. So to get this get this relation between these target variable and other variables, we use data visualization. Okay. So the first plot is called scatter plot. Okay. So why do we use scatter plot? No, because we use scatter plot in the times because we can see, like, using scatter plots we can see the pattern of the data, like how it's flowing in the data, and due to that pattern we can get inference, like from where to where, what are the intervals of the data, on how, in which pattern it's going, is it linear or non-linear, is it positive, and by this pattern we can say it's positive correlated or negative correlated. So as we can see here, I drew a scatter plot between mpg and displacement. So what is it? What is it? Mpg means miles per fuel consumption to versus displacement. So as you can see here, the vehicles which are going 100 displacement have more miles per gallon, have more consumption. The vehicles which have gone 400 like that have very less mpg. So by this we can tell that, uh, uh, as you can see the pattern flows like this, and it is a linear pattern. If we draw a thing, and it's a linear pattern, if I draw a thing, and as we can see it is like negatively correlated, which means inversely proportional. mpg is inversely proportional, because if the mpg increases, displacement decreases. So this one plot I've drawn between displacement and mpg, and there is another plot I've drawn between horsepower and mpg. As we can see here, see, mpg is more when the horsepower is less. Like if the horsepower is 100 like that, we have more mpg, 150 to 100. And if the horsepower is greater than 150, the mpg is, we can see that mpg is stuck at 20. So as we can see this is also the pattern the data tells us it is negatively correlated, and it is also a linear, and it is, we can say it is inversely proportional. Like if the mpg increases, horsepower decreases, as we can say. So this is the use of scatter plot. We can tell the what is it called, relation and the pattern of the data, how it's flowing through. So the second plot I've chosen is a bar plot. So the bar plot, the main thing in the bar plot is called, where what is it? The main thing in bar plot we can know that it gives us the relation between numerical variable and categorical variable. So whereas in scatter plot we can draw the we can have the scatter plot between numeric, tells us the relations only between numerical variables, but in the bar plot it tells us the relation between numerical variable and categorical variable over a period of time. So this is the main thing. So so to make a variable categorical variable, I'm what is it called, I'm converting into them as factors, as I'm saying here. So the am cylinder, vs gear, I'm converting these as factor using as factor. By using this command, I'm converting into categorical variable. See, I've converted everything into categorical variable. Now down, I've drawn a bar graph. I'll show you. Using the help of ggplot, I'll tell you what the ggplot, what is meant by ggplot and what are the thing in that. So see, so first we'll go with the ggplot. To know the ggplot, what should be the question mark ggplot. If we apply this, we might get what is ggplot. Wait one, give me a second. So okay, we will get the ggplot here. So what is a ggplot? It can be used to declare the input data frame for a graphic and to specify the set of plots, its aesthetics intended to be the common throughout all subsequent layers, especially overridden. Okay, so what are the um, parameters in it? So first one is the data, which is data set, and second is mapping. So mapping is nothing but default list of aesthetic mappings to use a plot. If not specified, must be supplied in each layer added to the plot. Other arguments to be passed. So aesthetic means, uh, like we should give the variable, which variable we want in the in every layer. Okay. So this is aesthetic. This is a aesthetics. So this is about ggplot. So with using the ggplot, we are doing this, and I'm using fill here. Fill is nothing but you can see aesthetic. I gave cylinders, so it is including cylinders, and the graph which I've drawn between is cylinders and the car count, like which cars are more, like if the 4-cylinder cars are more, or 6 cylinders cars are more, or 8 cylinders cars are more. And the fill is nothing but transmission. Means, see, zero is, as we already talked, zero is an automatic car and one is manual car. So automatic cars are more with 8 cylinders. So like this, we can take inference. Like you can see this. See, uh, in 6 cylinders, automatic cars are less, whereas compared to the manual cars. So by this inference, we can get if the people are using more automatic cars or lesser automatic cars, varying with the cylinders. Okay, and this is a bar plot I've drawn, and I've drawn this faceting plot. This is also an important graph. It gives us a subset which is called as small multiples. Like in a whole, in a big picture, we'll get the grids of charts. So in these charts, we'll get a bar plot. So each chart is a subset. Like, see here, I've drawn between the same thing which I've drawn upside. See, which the AM is nothing but transmissions, which is manual or automatic. One is automatic and zero is manual. So as we can see here, 3 gears, the number of gears, if 3 gears are, there are 3 types of cars, like which are having 3 gears, 4 gears, and 5 gears. And each gear car is having either 4-cylinder or 6-cylinder or 8-cylinder. So we can take an inference from this. In 3 gear cars, 8-cylinder, more cars are having 8 cylinders, and which are fully manual. So by this, what we can take, so the 3 gear cars are fully manual, they are not automatic. This inference we can take, and we can uh, do an analysis on this data. So like this, we are using this. And the thing is, next thing is box plot. So the basically box plot is very important part. So by this, we can take many inferences. Like, see, first of all, I've drawn a box plot between MPG and cylinders. So what I've drawn, and for manual cars and automatic cars, both I drawn. Okay, see, from this we can see this. So as we can see this, MPG is more for this thing. So MPG is for more for automatic cars. Okay, automatic cars which are the automatic cars which have 4 cylinders are only highest, not the 6 cylinders, not the 8 cylinders. So what does this plot gives us? This plot gives us C. So the plot starts from roughly 26. So automatic cars which are having 4 cylinders gives mileage starting from 26 to the maximum it is giving 32. So this black line is the mean. So average mileage given by a automatic car which are having 4 cylinders. So these much information we can gather from box plots. So this information I took from the box plot and noted it down. And one more main thing in the box plot, we can have outliers. As my data set is small, I do not have any outliers. And the outliers are clearly, we can see that outliers are clearly mentioned in the box plot in the form of a circle or something else, in the form of a circle, by which we can take out the outliers, which gives us the better prediction of the data set model. So the same box plot I've drawn for miles per gallon and weights. But here, I've taken for categories mm, cylindrical shape, if the engine shape is cylindrical or straight. So see, as we can see is this dot is called outlier. So by this, we can tell that the weight of the car the weights of the car are the less weights, the less weight of the car, more MPG, and the MPG uh, is more for cylindrical ones, not the straight ones, as we can see this. So this inference I can gather and I can give to the give for the take for the data analysis from the data set. Okay. And then the last but not least, it's a correlation plot. So again, to run the correlations, I have to first I have to convert the category factors as numeric. Okay. Because the correlation will be only given for the numeric variables, not the categorical variables. So I'm running the correlation. I'll tell you what correlation is. So basically correlation means the relation between one variable with the another variable. Are they directly proportional or indirectly proportional? For instance, we took in the scatter plot that if the horsepower increases more, the MPG will be less, the fuel consumption will be less. So like that, see, if as we can say, dark blue color is 1 and red color is -1 and others as follows. Like you can see, take one, for example, like displacement, take displacement versus miles per gallon. So what is it? Displacement versus miles per gallon now. It is red. Red in color means 0.7 minus 0.75. So they are inversely proportional. Like more the displacement, less the MPG. So like that, we can get the correlations and tell which variable is more significant and which is not. So this is about the data visualization. So next one, I'm going to tell about the fifth chapter, which is like in which I'm gonna perform central limit theorem on my data set. Now going into it. Now, so just for like whether to see my MPG variable is continuous or not, I perform two steps like is numeric command is to see whether the MPG variable is continuous or not. So the next thing which I did is plotting the density, plotting the MPG variable using density, which gives the normal curve density PDF of my MPG. See, as you can see, is numeric means yes, numerical values are to be numerical values are called continuous variable. So I plotted the PDF plot here of MPG. Same in the histogram also I plotted this. So now I'm going to perform like central limit theorem on my data sets on MPG. So what is central limit theorem? Basically it is a heart of hypothesis testing. The central limit theorem is useful when analyzing large data sets because it allows one to assume that sampling distribution of mean will be normally distributed in most cases. This allows for easier statistical analysis and inference. So given a data set with unknown distribution, the sample means will approximate the normal distribution. The sample should be sufficient in size. The distribution of sample means calculated from repeated sampling will tend to normality as the size of your sample gets larger. Means irrespective of the what is it called distribution of irrespective of distribution of variable, the central limit theorem will gradually turn it into a normal distribution. So means after turning it into a normal distribution, we can use it for hypothesis testing, statistical inference, something, many tests like that. So the central limit theorem has both statistical significance as well as practical applications. Analyzing data involves statistic methods like hypothesis testing, constructing confidence intervals. These methods assume that the population is normally distributed. In case of unknown or non-normal distribution, we treat sampling distribution as normal according to central limit theorem. If we increase the samples drawn from the population, the standard deviation of sample means will decrease. This helps us to estimate the population mean much more accurately. Also, the sample mean can be used to create the range of values known as in confidence band intervals. So the assumption behind the central limit theorem, data must follow the randomization condition. It must be sampled randomly. Samples should be independent of each other. One sample should not influence the other samples. Sample size should not be more than 10% of population. When sampling is done without replacement, the sample size should be sufficiently large. Now how we will figure how large this size should be. It depends upon the population. When the population is skewed or asymmetric, the sample size should be large. Okay. So now see, we are calculating the population mean of M, and we are creating a histogram of that. And this is the mean line. This red line is the mean line. The first initial graph we have is this histogram. So after this, we are making 9,000 iterations and taking a 10 sample size from that, then running the same thing. See, as you can see, it is slowly turning into a continuous variable as slowly the bell curve is coming. So more, if we take the sample size more and more, the perfection in the bell curve will be super. So this is the, as we are taking sample size 30, 50 and 500, we're taking the means, we are iterating it for 9,000 times. Now we are giving our, see, now it comes as super good bell curve, which indicates the normal distribution perfectly of our variable. By this, we can say that if we test this, the data set will be normal, the variable will be normal. If the variable is normalized, it shows normality, then we can perform tests like hypothesis testing and all. Next, we'll be going to 8th chapter where we'll conduct test on one sample test and one sample t-test and two sample t-test. About I'm gonna conduct two tests on my data set, which is one sample t-test and two sample t-tests, which I came across in 8th chapter. So what are these tests and why are we, what is that called? Why are we conducting them? So first, one thing, one sample t-test is a statistical procedure where you wanted to test where your population mean is different than a constant value. So for example, if your school wants to test that average mean of GPA for grad students is 3.0, they will use one sample t-test to uh, get it whether it is equal to 3 or less than 3, whether or greater than 3. They'll use sample to one sample t-test. And coming to the two sample t-test, it is all the same statistical procedure where you're interested in testing whether two whether these two populations have same mean or a different mean. In same example, if the school is interested in testing the average GPA of what is it called, major branch and arts major is same, science major and the arts major is same or not same, they want to conduct the test, they may use two sample t tests. So these are the basic so these two tests I wanna uh, what is it called, perform on my data set. So first thing, to perform I need to know the confidence interval. So to calculate the confidence interval, we need the following steps. First one, we need to calculate the mean. Second, we need to calculate the standard error of the mean. Third, we need to find the t-score corresponds to confidence level. Fourth, calculate the margin of error and construct the confidence interval. So first thing, see MPG. For MPG, I'm considering mean. Now I'm running it. Applying, I got 20.1 is the mean of my data set. Now, the SD command can be used to find the standard deviation. I should find the standard deviation. The length command can be used to find the sample size. Now, length, this gives me the sample size. SD gives me the standard deviation. I'm dividing the both to get the error, standardization error, which is 1.07. Now, finding t-score that corresponds to the confidence level is step 3. We need to have probability alpha by 2 probability in the lower and upper tails. We need to divide by 2 because there are two tails. The Qt command will calculate the t-score. Okay. So alpha will giving us 0.05. Degrees of freedom, we are giving sample, like how many rows will be there, -1. And then t-score will be given by this formula. And we're printing it. We got the t-score as 2.04. Now calculate the, we are calculating the margin of error and constructing a confidence interval. Okay. So margin error is given by t-score into standardized error. So we're creating two bounds, lower bound and upper bound, and we're printing it. I'm running it for you. It gives 719 to 22.3, which is our confidence interval. Okay. So What is one sample data set? We were given a, now I'm taking this as my problem statement. We'll be using MTCAS dataset to test hypothesis. The average miles per gallon for cars in the dataset is 10 mpg. If it's 10, then it's null hypothesis, or it's high alternative hypothesis. Okay. So to conduct a t-test, we need following tests. So calculating the mean again, calculating the standard error of the mean, calculating a t-score for sample mean, that which is distance from the hypothesis mean, and fourth one is calculate the p-value and for the t-score. Okay. So step 1 and step we already did in the above comment. So completing step 3. So directly we will be calculating the t-score for sample mean, given mean, which is 10. Okay. And this sample mean we'll get it from the second step. So we have we got the t-score, which is 9.47. Okay. Now calculating p-value for the t-score. Here the pt command is used to find a probability of a t-score as far or farther away from 0. To make things a little simpler, we use the ABS command, absolute value command, to ensure the t-score is positive. Finally, this is a two-sided test, so we need to multiply the value by 2. Okay. So if we are doing the two-sided test, we're getting 1.15, the p-value. No, p-value power minus 10, which is very low, means, and 15. We are calculating the p-value for one-sided test. We saw for the two-sided, now we are calculating for the one-sided for less than 10. Means connecting a t-test to determine if MPG is greater than 10. Now we are seeing if it's greater than 10 or no. Yes, we got the p-value low again. When we are seeing if MP, we are conducting a t-test to determine if MPG is less than 10. We are getting p-value greater than 1, which is pretty high, which is not good. So finally, we are using the t-test of everything, whether it's greater than 10 or not equal to 10 or greater less than 10. And we are giving it. So see, for not equal to 10, we have p-value very less. So then it is alternative hypothesis. True mean is not equal to 10. P-value is very less. And whether to greater than 10, even the p-value is less here. True mean is greater than 10. Okay. And last but not least, the p-value is 1. True mean is less than 10. So these all gives us alternative hypothesis. This means the population mean is not equal to 10, which we are getting from the one sample t-test. Now going to two sample t-test. We'll be using MTCAS dataset to test the hypothesis. The average miles per gallon for cars with automatic transition is different from the cars with the manual transitions. Means he's giving MPG of automatic is equal to MPG of manual. This is null hypothesis, and which is alternative is vice versa. To conduct a t-test, we need to the following step. One, we need to plot the data. Second, we need to use the t-test. Okay. So plotting the data, as we know, the already box plot. I'm just running for you this. So as we can see, it is very clear the population mean for both automatic and transitions are 0. So that now we are running a t-test. So I'm running a t-test, giving the confidence interval value as 0.95. See, in t-test, we're running p-value is very less, and true differences in mean between group 1 and group 2, which is not equal to 0, means it is alternative hypothesis. So this is what we are testing, hypothesis testing on our data variables. Next, we'll be going to the linear 11th chapter, in which I did linear regression. Now we are going to perform linear regression on our data set and building a model. So what is the linear regression basically? So linear regression, why do we do it? Because it tells us the relationship between two variables, and we can predict the value of one variable using the another variable using linear regression. Means, see, the two variables should be linearly dependent, and then if they are linearly dependent, the linear regression model will gives us the best accurate prediction. So in this, I'm taking the problem statement as C. In this there will be two variables. One variable I'm taking as weight, and second variable I'm taking as MPG. So I'm taking as you can see here, and plotting the graph and adding a regression line there using the command ab line lm. This is least squares, or this is linear model command. So I'm running it. As you can see the data miles per gallon is negatively correlated to the weight. Means as more the weight goes, the miles per gallon decreases. It is in the negatively correlated way in a linear form. So they both are linearly related in the negative correlated way. Then, as you can see the scatter plot from above, there is a negative correlation between MPG and weight. As weight increases, the MPG of car goes down. So as we can see, what is the correlation value? As we can see, it is minus 0.8. So finding the correlation between, the stronger the association of two variables, the closer the Pearson correlation coefficient R will be either +1 or -1, depending on whether the relationship is positive or negative. I told you. Then we are applying a linear regression model to our data set, to our problem. So we are applying it. As then we can see the summary of our model. As we can see, the weight is significantly important, and we have a RSC error here, which is 3.05 on 30 degrees of freedom. We have multiple R squared error 0.753. We have a static error 91.4. We have p-value, which is 1.1 equal minus 10. So LM stands for linear model. The code reads as MPG is explained by the way. The data we are using to create this linear model is from MTCAR data frame, as we know. So now see, we built a model which can predict the data of one variable using another variable. So I'm taking unseen, a variable, new variable which has already weight value as 4. Using this weight value as 4, we have to find the prediction of our model, which gives the MPG. As I run this, so it gives for 4 weight, our model predicts the MPG will be 15.9 gallons. So now in this we are going to do residual analysis. So basically, residual plots are generated by the regression function, which can be used to validate that some of the assumptions that are made about data set indicating it is suitable for a linear regression are met. There are a number of assumptions we made about data that must be met for a linear model to work successfully, and the standard residual plots can help validate of them. And some of the assumptions are the dataset must have some linear relationship, and it should have multivariate normality. Means dataset variables must be statically normally distributed, resembling a bell curve. It must have no or little multicollinearity. This means the independent variables must not be too highly related or too lowly. No autocorrelation. Autocorrelation occurs when the residuals are not independent from each other. For instance, this typically occurs in stock prices and all. And homoscedasticity, meaning the residuals are equally distributed across the regression line, above and below the regression. The variance of residuals should be the same for all predicted scores. So basically, there are 4 standard plots with fit variable once the model is generated. These can be used to show if there are problems with the data set. The model produced these plots are residuals versus fitted plot, normal Q to Q plot, scale location plot, and residuals versus leverage plot. Okay. We've using the MTCAS dataset, we used the regression function to fit a regression line and then plot to see it result. The plot graphically shows the side of residual value using color code. Green smaller size and blue is larger size, I guess. Okay. The size of the residual is the length of vertical line from point where it meets. See now, here I have fit the model, saved the predicted values, saved the residual values. Using these two values, I have plotted a graph. I'll plot the graph. This is the graph I got. This is the regression line I fitted, and these are the residuals. These are the residuals, which means these are the this is the residual length, which some of the data points are how much they are far from the residual regression line. So we'll get the summary first. as we can see, look in summary, it has p-value of 1.294, which indicates that there is highly statistical significant relationship between the two variables, means it's closer to zero. So why? So then why do we look at, why do we look, we need to look at the residuals. So why basically why are we doing this analysis? P-values by themselves can potentially be misleading without analysis of residuals. We know that. Residual plots are used to look for underlying patterns in the residual that may mean that the model has a problem. When using the plot function, the first plot is residuals versus fitted plot. Gives an indication if there are non-linear patterns. For a correct linear regression, the data needs to be linear. So this will test if the condition is met or not. So as we can see, when we look at the plot below, we see that the data does not have any obvious distinct pattern. While it is slightly curved, it has equally spread residuals around the horizontal line without a distinct pattern. This is a good indication it does not have a non-linear. As we can see here, it is slightly curved, which does not have a non-linear. Okay, I'm running this residual versus fitted plot. As you can see, we got the plot, nice plot. Residuals should be normally distributed, and the QQ plot will be show this. If the residuals follow to a straight line on this plot, it is good indication that they are normally distributed. For our model, QQ plot shows pretty good alignment to the line, with a few points at the top slightly offset, probably not significant, but a reasonable alignment. I'll run it for you. See, it is a good fit actually. So, next one. This plot tests the linear regression assumption of equal variance. That is, that the residuals have equal variance along the regression line. It is also called spread locations plot. So what does this mean? The residual have equal variance, occupy equal spaces above and below the line. So I'll show you as I print it. As you can show, okay, it takes the equal and almost okay. Few points are going there and here, but it's fine. It's fine. We have a good deal with it. So next plot. This plot can be used for influential cases in this data set will affect the model. So its inclusion or exclusion can be considered using this plot, leverage plots. Okay, this an influential case may or not be an outlier. It can be or cannot be an outlier. The purpose of this chart is to identify cases that have high influence in the model. Outliers will tend to exert leverage, with therefore influence on the model. The plot for empty example shows, wait, I'll show you the plot first. We'll see the plot. See, as we can see here, outside Cook's distance, but it is really barely inside the line. So its inclusion needs to be considered in the model. So as it does not, okay. So summary, what is the thing we are getting from residual analysis? Residual analysis plot are very useful tool for assessing aspects of veracity of linear regression model on particular data set and testing the attributes of a data set meet the requirements for a linear regression. Next, we'll be going to ANOVA testing. So now we are coming to the ANOVA testing. So this is the last test I want to run on my data set. So first, basically, what is ANOVA testing? ANOVA is also known as analysis of variance, which is used to investigate relations between categorical variables and continuous variables. Categorical variables means which have classes like, see, if the cylinder shape is, it should be either cylindrical or straight. It is a category. This is called a categorical variable. And continuous variable, it is a numerical variable. Means it has various numerical values in the data set. Okay, that is the main difference between categorical and continuous variable. It is a type of hypothesis testing for population variance. So first thing, what ANOVA test setting up? What ANOVA test involves setting up, like null hypothesis means where all population means are equal. Alternate hypothesis, at least one population mean is different from another. So this we are setting up in ANOVA testing. Like we have to tell whether it is null hypothesis or alternate hypothesis. So there are two tests in ANOVA, one-way ANOVA and two-way ANOVA. In one-way ANOVA, we'll take one categorical group into consideration. In two-way ANOVA, we'll take two categorical variables into consideration. So now let's perform one-way ANOVA test. So performing one-way ANOVA test. One-way ANOVA test is performed between displacement attribute and a continuous, which is a continuous attribute, and a gear attribute, which is a categorical attribute. Okay, gear have categories like 3 gears, 4 gears, 5 gears. Okay, so first we have to install a package called DPLYR, which is useful for box plot and ANOVA. So box plot, we are plotting between displacement and gears, and gear is considered as a factor because it's a categorical variable. Step 1, set up null hypothesis and alternative hypothesis. Okay, now step 2, calculate the test statistics using AOE function. AOE function is nothing but our ANOVA function. So using ANOVA function, now we are doing, and we are printing the summary of it. I'll discuss the summary results now later in the figure. Now step 3, okay, come. So I'm gonna run it now. Wait, let me run it. So I've ran it. It ran successfully. So now coming to the box plot. See, gear has 3 categories: first category, second category, third category. So in these categories, we can see the mean, population mean here. Means for the gear, one gear car, the displacement, the mean displacement is at 320. So second gear car, the mean displacement is at 150. Third mean car, the mean displacement is at 170. So with this mean displacement, now we are going to the summary. What is the summary? See, as we can see the summary, the box plot show the mean values of the gear with respect of displacement. And here the categorical variable is the gear on which the factor function is used, and continuous variable is displacement, which I already told you. Now, the summary shows, what does the summary shows? See, the gear attribute is very significant to displacement. Why? Because as you can see in the summary, it has 3 stars. 3 stars indicate more and more significance. See, okay. And also p-value is less than 0.05, as we can see here. P-value is less than 0.05, as we can see here. And then wait, and also the p-value is less than 0.05, so proves the gear is significant to displacement. That is, it is related to each other, and we reject the null hypothesis as the population mean are different from each other. That's why we reject the null hypothesis. And p-value is also less than 0.05. So now coming to the two-way ANOVA testing R. So what is two-way ANOVA test? Two-way ANOVA test means we are taking 2 categorical variables into the consideration with a continuous variable. So it is performed between, again, the displacement attribute, which is a continuous attribute, and the gear attribute, which is a categorical. And third one attribute is AM. AM is nothing but transmission attribute, whereas there are 2 categories in AM. One is automatic transmission, and another one is what is it called, manual transmission. So again, we are performing the same thing here. One thing is we are installing the package again, and we are loading the package DPLYR in the box plot. As you can see the box plot, I'm drawing between displacement and gear, and this is the data. It is empty curve which I'm using, and the subset. See, as we are taking the second category into consideration, we have to put the second category into graph. So how can we put, like, how can we categorize? We are using the subset parameter in box plot. This is an important thing, and others all you know in that set. And also I'm calculating AOV ANOVA test using AOV AOV command in the displacement versus factor. Why we are using factor? To convert it into categorical variable, which is empty car gas, and into empty cars transmission thing. And now we're printing out the summary. Okay, so I'm printing it out. 1 second. So I ran the code. So coming to the box plot, that the box plot shows the mean values of gear with respect to displacement. Here the categorical variables are gear and AM on a factor which is used, and continuous variable is displacement, as you can see it. And this thing, and let me see once. Give me a second. See, as in summary shows, the gear attribute is very significant to displacement. As we see in the summary, and the gear have 3 stars, which is more significant. But whereas automatic transmission variable doesn't have any stars, so it is not that significant. See, as you can see here, AM attribute is not much significant to the displacement. The p-value of gear is less than 0.05, as we got earlier. When 3 stars means, as you can see, it has 0.001. So it proves gear is significant to displacement, that is related to each other. P-value of AM is greater than 0.05. There's no stars means it is greater than 1. It is greater than 0.05. It is not significant to displacement. They are not related to each other at all. So by this, what we can see, displacement is strongly related to gears in car. That is, displacement is dependent on gears with p-value is less than 0.05, and displacement is strongly related to gears but not related to transmission mode in cars with p-value greater than 0.05 with AM. So by this ANOVA test, we can, what we can get is, we are the first thing is like we are checking if the null, if it sets up null hypothesis or alternative hypothesis. And second thing, the main thing is we find out the relation between categorical variables and continuous variables. So this is the main motive of ANOVA testing. Okay, and due to this testing, we can infer that whether we can reject null hypothesis or accept the null hypothesis. So thank you. Thank you for giving me opportunity to present my project here. Thank you. My presentation ends here.